Hi, this is my presentation on carbidopa and how it works. First, let me explain Parkinson's disease. This is a chronic and progressive neurological disorder that primarily affects movement. It's caused by the degeneration of dopamine-producing neurons in the brain. And dopamine is a neurotransmitter that regulates movement and coordination. So when it's depleted, that's what causes the symptoms of the disease. The exact cause of the disease is unknown, but it's believed to involve a combination of genetic and environmental factors. And there's currently no cure, but there are treatments such as medications and surgical interventions that can help manage the symptoms of it. These symptoms of the disease, there's some primary ones such as tremors, which is when it starts in a limb like the hand or fingers, even when the hand is at rest, and it's just the shakiness of it. And bradykinesia is the slowness of movement. Rigidity, which is the stiffness of the limbs, muscle aches, and decreased range of motion. And postural instability, which impairs your balance and coordination. There are also secondary symptoms such as speech and writing issues, loss of automatic movements like blinking and the swinging of your arms while you walk, and just general decrease in motor functions. Now, carbidopa is a medication that's used to treat Parkinson's disease. The way it works is it enhances the efficiency of levodopa by increasing its availability in the brain. And when taking this drug, it reduces the side effects of Parkinson's disease, and it's often administered in combination with levodopa in a single medication called Sinemet to optimize the treatment of the symptoms of Parkinson's. Now, the structure of carbidopa is shown in that picture on the top, and to explain it, it has a hydrazine moiety which interacts with the enzyme's active site, preventing it from converting levodopa to dopamine. There is a benzyme ring with two hydroxyl groups, and this facilitates its interaction with biological systems involved in dopamine metabolism. There's an alpha methyl group, which enhances the specificity of carbidopa for AACD or AADC, and there's an alpha hydrazino substituent, which contributes to the inhibition of the enzyme by forming a stable hydrazone bond with the PLP cofactor in AADC, which ultimately inhibits its activity. And overall, it has a backbone structure of an amino acid, and that helps it mimic substrates and interact effectively with the decarboxylase enzyme. So the way it works is, and it's also shown in this picture on the right, but it inhibits the enzyme aromatic L-amino acid decarboxylase, which is just called AADC, outside the brain, and this is responsible for converting levodopa into dopamine. And since dopamine can't cross the blood-brain barrier, this conversion reduces the amount of levodopa that reaches the brain, which limits its effectiveness. And by inhibiting this conversion, carbidopa ensures that more levodopa reaches the brain, where it's converted into dopamine to alleviate the symptoms of Parkinson's disease. Carbidopa itself does not cross the blood-brain barrier, so it doesn't affect the central nervous system directly. Now, X-ray crystallography is a common technique used to determine the three-dimensional structure of molecules, mostly small organic compounds like carbidopa and large biological macromolecules like proteins and nucleic acids. What it's used for is to help scientists understand how drugs like carbidopa function at a molecular level, and it's able to show you a 3D structure like this one shown on the right. That is carbidopa's structure, which is a combination of planar and tetrahedral geometries, which is what gives carbidopa the unique shape it needs to fit into the enzyme's active site. Now, the process of how X-ray crystallography works is it starts with crystallization. So the protein or small molecule that's being used is crystallized. Then diffraction, which involves a beam of X-rays directed at the crystal, which pass through the crystal and are scattered by the electrons in the atom, which create a diffraction pattern. Then this pattern is collected by rotating the crystal and capturing multiple images from different angles. And then that resulting data includes the intensity and position of each spot, which is then processed using mathematical algorithms to convert the 2D diffraction pattern into a 3D electron density map, which fits the atomic structure into it to create a model of the molecule that represents the distribution of electrons within the crystal, which is like the one in the last slide of carbidopa that I showed. In conclusion, carbidopa and X-ray crystallization or crystallography and all of these tools are crucial for developing and optimizing treatments of Parkinson's disease because understanding the mechanism of carbidopa helps in optimizing dosages and combinations to maximize therapeutic benefits and minimize the side effects that it can cause. And knowledge of carbidopa structure and how it interacts with the AADC enzyme would also help design new drugs that might be more effective than the Simonet that's already used. Also, it would help advance scientific research because X-ray crystallography has been crucial for determining the structures of numerous biomolecules. And it would also improve patient care because developing more effective therapies would potentially slow the disease progression or even help find a cure for it. So overall, it could just enhance the quality of life for individuals with Parkinson's disease and any other related conditions that it would help. And then here are my sources.